Okay, continuing on here. So we're on number 6 now. Find the value of z sub 0.20. So this is just a little quirky thing that'll show up later on in chapter 9, I think. So z sub 0.02, or sorry, it was 0.20 like that. So this is something that we call z sub alpha with a little subscript there. All this is it's asking the same questions that we were just looking at. If we have the mean at 0, z sub 0.2 is looking for the z-score where the area to the right is 0.2. So it has to be out here somewhere, and if I look at the area in this tail, that represents 20% or 0.2, which means that if I'm trying to find this z-score, we're going to do another inverse norm. So second, distributions, inverse norm. The area to the right is going to be 80%, and then the mean is still 0, standard deviation is still 1. So we get 0.84. So z sub 0.20 is 0.84. Okay. It's just the z-score that cuts off the top 20%. All right, moving on. So I'm going to skip over these because these are really the same exact question. It's just that now we're not looking at the standard normal distribution. We're looking at other ones. So hopefully you guys can figure those out. I want to get to the word problems. So let's start with this one. Maybe we'll do 2 word problems here. So number 10, tire wear. Suppose that Dunlop Tire manufacture a tire with a lifetime that approximately follows a normal distribution with mean 70,000 miles and standard deviation 4,400. A, what proportion of the tires will last at least 75,000? So A, what proportion of the tires will last at least 75,000 miles? Okay, let's go on over here. So this is number 10. Okay, so whenever you have these questions here, and the big key that you know is going to be a chapter 7 question is that it gives you the mean and it gives you the standard deviation and it specifically says the word normal distribution. As soon as you see that, go ahead and draw the standard, the regular normal distribution for this question. So we have our bell curve where our mean is at 70,000. And then what you can do, you don't have to do this, but you could add 4,400 up 3 times and subtract 4,400 down 3 times. I'm not going to do it here because it would be too cluttered. Okay, so A, what proportion of the tires will last at least 75,000? At least 75,000 is 75,000 or more. So if 70,000 is in the middle, 75,000 is going to be out here to the right. And we want to be at least 75,000, which means that we want to be at 75,000 or anything bigger than that, which means that we're trying to find this area of my normal distribution. Okay, putting up the calculator. As soon as you know what area you find, go ahead and go to the normal CDF of the calculator. So again, it's asking for the lower limit, the upper limit, the mean, and the standard deviation. For my area here, my lower limit is starting at 75,000. My upper limit is going to infinity, so we'll type in that 1E99. The mean of this is 70,000. The standard deviation is 4,400. Okay, paste, enter. And then that's it. So that's going to be our answer. So the question is, what proportion of tires lasts more than 75,000? Around 12.79%. Or most of the time they just want you to leave it as a decimal, so 0.1279. Okay, that's part A. Let's look at part B. So part B. Suppose that Dunlop warrants the tires for 70,000 miles. What proportion of the tires will last 60? Or sorry, I said 70,000. I meant 60,000. I'll start over. Suppose that Dunlop warrants the tire for 60,000 miles. What proportion of the tires will last 60,000 miles or less? Same kind of deal here. So I'm just going to redraw the picture. 70,000 is in the middle. 60,000 is going to be out here to the left, and we want to be 60,000 or less. So we're going to the left. Again, that's asking for the area. So we're going to go to our calculator, second distribution, the normal CDF. This time we're going to negative infinity because it's going to the left forever on our number line. It's going up to 60,000 and stopping, so that's my upper limit. The mean is still 70,000. Standard deviation is still 4,400, and then we'll paste, hit enter again, and we get our answer. So the proportion of tires that will not get to the warranty is around 1%, 0.0115. Which is good for that company, right? That means that a very, very small proportion of these tires are actually going to not reach the warranty. All right, moving on to C. What is the probability that a randomly selected Dunlop tire lasts between 65,000 and 80,000? So again, just to do this real quick, graphing it out, 70,000 is in the middle. I already forgot my two numbers. It was 65,000 and 80,000. So 65,000 is going to be here to the left of 70,000. 80,000 is going to be to the right, and we want to be in between these two numbers, and we're trying to find the area again. So same thing, second, distributions, the normal CDF. This time the lower limit is at 65,000. The upper limit is at 80,000. Mean still the same, standard deviation still the same. Paste, enter, we get 0.8606. So the proportion of tires that last between 65,000 and 80,000, 0.8606. All right, one more question for this one. D, suppose that Dunlop wants to warrant no more than 2% of its tires. What mileage should the company advise as its warranty mileage? So this kind of goes back to Part B a little bit. Remember with Part B, 60,000 was about a little over 1%. Here we want to be at 2%. So suppose that Dunlop wants to warrant no more than 2% of its tires. Drawing it out. So we have our thing, 70,000 is still in the middle. What we want to find is we want to find the bottom 2%. So somewhere out here is a value. We don't know what that value is, but we do know that the area to the left of that value is 2%. Whatever this value is the answer to the question. So we're going to go to our calculator. This time it's different because this time we know the area and we're trying to find the data value. So we're going to do the inverse norm instead. The area to the left is 0.02. The mean for this is 70,000. If you go back to the question, the standard deviation was 4,400. Paste. And we get our number. So 60,964. I'll round it to there. 60,964. That is the amount of miles that 2% of the tires have less than. Or last less than 60,964. Okay, let's do one more question, and then I'll probably end these videos. Let's see, you got number 11 here. Something about IQ stuff. Or baseball. How can I give up baseball? No, I kind of don't like that question, though. Let's see about number 13. Reading books. Just kind of skimming over and make sure we can all do it. Yeah, it looks all right. All right. According to a Gallup poll, 46% of Americans 18 years old or older stated that they had read at least 6 books, fiction and nonfiction, within the past year. You conduct a random sample of 250 Americans 18 years old or older. Verify that the conditions for using the normal distribution to approximate... Oh, you know what? I read it and I skipped over that part, which means that this is section 7.3 stuff, which is not stuff we're doing. I guess let's go back, and I guess we will do the baseball problem. All right, sorry about that. 12. According to Major League Baseball rules, the ball must weigh between 5 and 5.25 ounces. A factory produces baseballs whose weights are approximately normally distributed with a mean 5.11 ounces and standard deviation 0.062 ounces. What proportion of the baseball produced by this factory are too heavy for use by the Major League? Okay, so going back over to our notes here. This is question 12, part A. Again, it has everything we need for the normal distribution stuff. So we're going to draw our normal curve. This is the factory's baseball stuff. It has a mean of 5.11. That's what it sets to be the mean, with a standard deviation of 0.062. A ball is too heavy if it weighs more than 5.25. 5.25 is out here to the right of 5.11, and we want to know the proportion of baseballs that are too heavy that are bigger than 5.25. So we're going to go to our calculator. We're looking for an area, so our second distribution's normal CDF. The lower limit for my area starts at that 5.25. the upper limit is going to end at the infinity, so 1E99, just simulating infinity. These baseballs have a mean of 5.11 and a standard deviation that I think was 0.062. I'm going to double check that. Yeah, 0.062. Okay, good. So lower limit, upper limit, mean, standard deviation. We're going to paste, hit enter, and we get this number, 0.01197. So just rounding that out. Oops, wrong button, sorry. This would round to 0.0120, and that's going to be our answer. So roughly 1.2% of all of the baseballs that this company makes are going to have to be thrown away because they're too big for major leagues, or they weigh too much. Let's look at part B. Part B, what proportion of the baseballs produced by this factory are too light for the use by the Major League Baseball? So same thing, but this time when we draw our distribution, 5.11 is still in the middle. Remember that I think it was 5 on the dot. Yeah, 5 is the cutoff for being too small. So 5 is out here to the left, and we want to know the proportion of baseballs that are too light, so to the left of 5. So we're going to go to our calculator again, still that normal CDF. We're going to simulate it going to infinity to the left, so we're going to do -1E99 to simulate negative infinity. My upper limit is that my area goes up to 5. The mean is still 5.11. The standard deviation is still 0.062. So we'll just paste and hit enter. Here we get 0.038. So it's more likely that we make a ball that is too light than we make a ball that is too heavy. 1.2% compared to 3.8%. All right, let's see what else they got for us. C. C, what proportion of the baseballs produced by this factory can be used by Major League Baseball? So here we're trying to find the proportion that's in between the 5 and the 5.25. But I'm going to be a little bit clever here. If I know that 1.2% is too big and 3.8% is too small, that means that the amount that we can use is in the middle. So 100% minus the 3.8 that's too small minus the 1.2 that's too big, we end up with 95% that can be used. And we can double check that with the calculator. So if I do second distributions, this time I want to be in between 5 and 5.25. So my lower limit 5, upper limit 5.25, the mean and the standard deviation are still the same. This should be very, very, very close to 95%. So you see we get 0.9500. Okay? And then one more. If 8,000 baseballs are ordered, how many baseballs should be manufactured knowing that some will be discarded? This is a little bit more of an algebra question than it is a statistics question, but still cool. We know that only 95% of the baseballs that are going to work, which means that we have to make more than 8,000 because we know that 5% of the baseballs we're going to make just aren't going to work. So just to kind of map out what this algebra equation would be, and maybe you can figure out in your head with just some proportion stuff, but what we want is we want 8,000 as a result. What we know is that the number we make, we can only keep 95%. So I'm just going to take the number we make and multiply that by 95% and set that equal to the 8,000. Then I can just divide that 0.95 by the 8,000 to get my x. So whatever 8,000 divided by 0.95 is, 8,421. So we have to make 8,421 because we know that around 421 of the balls that we make aren't going to work, so we are left with the 8,000. Okay, great.